Hi guys, how are you all today? I am doing great here, so I hope it's the same thing out there. Well, today let's start with a new chapter called Units and Measurements. Well, say for example, your mom asks you to go to a grocery shop and she'll ask you to get some groceries. Okay, now you'll go to the grocery shop and you'll ask the shopkeeper to give you some rice. So he'll ask you how much. You'll think and you don't remember what exactly your mom told, you'll tell, okay, fine, give me 10 rice. The shopkeeper is quite confused. How do I give 10 rice? So what he'll do, he'll pick up 10 grains of rice and then he's going to give it to you. Okay, take 10 rice. So this is what you asked for. Now you're confused. If you take this 10 grams of rice, grains of rice, you will be definitely punished back home. So you'll take a while and think about it and ask the shopkeeper to give a bag of rice which is weighing about 10 kgs. Now the shopkeeper is very happy because you're making some sense. You're not asking for 10 grains of rice. Instead, you're asking for 10 kgs of rice. So he's going to weigh 10 kg and then he's going to give you. Now, what went wrong initially? You just asked for 10. That 10 can be anything. It can be 10 grains of rice. And later on, you specifically told you need 10 kgs of rice. So what is 10 here? It is just a number. 10 is just a number here. However, what is this kgs? Yes, you are right. This kg here is nothing but the unit we are talking about. I told you, right? Let us discuss about units and measurement. So this is the unit we are talking about. Okay. Now, let us take another example. Okay. So you're going to come to me and you're going to ask, ma'am, what is your height? So I will tell my height is 5'4". What does that even mean? You will start thinking, okay, what is this? Is it 5.4 centimeter? Or is it 5.4 meters? Or is it 5 feet 4 inches? Which is right. You'll start thinking. And then after some time, I'll tell I am 5.4 feet or 5 feet 4 inch. So here you can see that 5'4" is just a number. It actually does not have any significance. So if you just came to me and asked me what's your height, and if I told you I'm 5'4", what would you even think? What is she? As I told you, is it centimeter or meter or inches or feet? What is it, right? So here 5.4 is just a number, whereas the centimeter, meter, feet, these are the actual units. So what are these units? So units is something we measure of, okay? Whatever we measure, we are going to tell that in terms of units. Is that clear? Okay. Now, fine then, we learned about units. So what do we measure? That is the next very important question. What do we measure? What are the different things we need to measure, right? Right now, I gave you two examples wherein in first example, we measured mass and the second example, we measured length, isn't it? So we know that length is one of the things which we can measure. Apart from length, what is that we can measure? As we were discussing, we can measure mass. And apart from this, we can measure time, isn't it? Time is measurable. And we can measure temperature, mole. So what is this mole? So mole is nothing but the number of atoms, okay, the number of atoms in a given substance. Okay, I'm gonna brief about that later on. And we can actually measure the luminosity, right? We'll get to that as well. And we can measure current, right? So here we have length. So if we have to measure how long something is or how wide something is, we use length. And if we have to weigh something, then we are going to use mass, isn't it? And to see check the time, we use seconds, or we can measure time. And how cold or hot a particular substance is given by the temperature. Okay. Now coming to the mole. Mole is nothing but the number of atoms in a given molecule. Okay. That particular number is known as mole. Okay. You're going to learn about this very much in depth in your chemistry lessons. Now let us just know that it is simply the number of atoms in a particular substance, or number of particles in a particular substance. Okay. Next comes the luminosity. Luminosity is nothing but how bright a particular thing is, or how bright a candle is, how bright a tube light is, how bright the sun is, how bright the stars are. Okay. So this is measured by something called as luminosity. Okay. And I'm pretty sure you're very much aware of current. Okay. Current is measured with respect to amperes. So current is measured with amperes, whereas luminosity is measured by a unit called candela. Okay. It is measured by a unit called candela. And I'm pretty sure you're very much aware of the other units we use to this. Anyways, we are going to learn the same thing in depth in this particular class. Okay. Now, let us discuss about types of units. Okay. Let us just keep three basic measures in our mind, and with respect to that, let us compare the units, let us know which are the types of units we have. Okay. The very first one is CGS. That means centimeters, gram, and second. Now tell me, what will be, why do we need this unit centimeter? Definitely to measure length. Why do we need this gram? To measure mass. And the seconds we need to measure time. So CGS is one of the type of the unit. And next comes the FPS, which means foot, pounds, and second. Again, foot is with respect to length, pound is with respect to mass, and seconds, it remains the same. It is with respect to time. Okay. The second type of system is FPS. Okay. Foot, pound, and second. Right. And the third one is MKS. Here again, we are going to measure the same things, that is length, mass, and time. However, the unit is different. Okay. So what do we have the units as? We have meters, kilograms, and seconds. I'm pretty sure that you are very much aware of how much is 1 meter. So 1 meter is equal to 100 centimeters. And the bigger unit than meter is kilometers, and 1 kilometer is equal to 1000 meters. I hope you are aware of it. This is 1 kilometer. However, going further, when it comes to kilograms, again, kilograms is nothing but a higher unit of grams, wherein 1000 grams is equal to 1 kilogram. And then, as you can see here, repeatedly we use seconds to measure time. This does not change. We don't have any other scale to actually measure time. Okay. Wherever you go, it is going to be universal in nature. That is going to be 1 second. The measure is going to be 1 second. Okay, there's no change in that. Talking about universality, we have something called SI unit. What is this SI unit? This is nothing but International System of Units. Okay, so International System of Units are those units which are accepted worldwide. Okay, and MKS is said to be the SI unit of length, mass, and time. What does that mean? Wherever you go and tell it is 100 meters, or wherever you go and tell it as 1000 meters, that particular length remains same no matter in which country you are. Okay. Similarly, when it comes to kilograms, No matter in which country you are, the amount, that weight remains same. Okay, so this is known as the SI unit. Now, moving further, we have something called as base units, or these are also called as the fundamental units. So these are all the fundamental units which we are going to use further to derive other units. Let us talk about that a bit later. Okay, now let us understand what are the base units. So these base units are like the dimension of any measures. Okay, so talking about space, we have three dimensions, right? That is length, breadth, and height, or X, Y, and Z axis. Similarly, these 7 units, whatever you can see here, which are called as base units or fundamental units, are going to act as the dimensions of other units. Now, I have a question for you. All these quantities are measurable. Okay, are there any other set of quantities which cannot be measured? Think about it. Okay, say for example, I'll tell, wow, I'm very happy today. I'm very, very happy today. So can you actually tell how much happy you are? Can you give a number to it? Can you attach units to it? Okay, I am this time, or I am so and so and so happy. Can I tell that? Or can I tell, okay, I'm very sad. I'm 10 kg sad today. I'm 15 kg sad today. Can I tell something like that? No. Why cannot we do that? Because those are all known as the abstract quantities, whereas these are all the physical quantities. What are these physical quantities? These physical quantities are those quantities which can be measured. Whereas when it comes to all those happiness, sorrow, or confusion, or those sense of feeling or pain, all these are abstract quantities. We cannot actually measure them. We don't have a particular instrument or a scale to measure them. Whereas when it comes to all these quantities, we can measure them. Henceforth, we call them as physical quantities. Okay. Now, these are all physical quantities, and then these are all called as the basic dimensions of quantities. Why am I talking about dimensions here? Because I told you, right, other than fundamental or basic quantities, we have something called as derived quantities or derived units. So these derived units are derived from the fundamental units. It's very much in the name, right? Okay. Talking about their units, let me tell you the SI unit of each and every fundamental quantity. You know that the SI unit of length is meter. So I'll just write it as M here. So meter is represented by M, isn't it? Don't use this bracket there. It's just the meters M. Mass. So how do we weigh mass, or what are the units of mass? It is kg. It is the SI unit. Time is second. When it comes to temperature, it is Kelvin, capital K. And I hope you are very much familiar with other two scales as well. One being the degree Celsius, the other one is the degree Fahrenheit. Those two are the other two scales of temperature. However, here we are discussing about Kelvin, because Kelvin is the SI unit of temperature. Next, we have mole. We are going to write it as MOL. That is the unit. Next, we have the luminosity. Its SI unit is candela, which is represented by CD. And the SI unit of current is ampere. Very good. So it is going to be represented as A. So these are the main 7 physical quantities. Now, for us to go to the derived units, we have something called as dimensions of physical quantities. I was talking about it, isn't it? These are all called as the dimensions of physical quantities. Let us just go through the definition of it, okay? So dimensions of physical quantities means It is nothing but the power to which the base quantities are raised to represent the quantity. What does this actually mean? Okay, let us get back to the actual previous slide for you to understand. We have all these quantities here. So these are all called as the base quantities. And whenever we represent all these base quantity in combination with other to represent another new quantity, we are going to call that as the dimensions of physical quantities. And then those dimensions of physical quantity, whatever you have represented, that is going to be called as the derived quantities. I hope I'm clear so far. So usually these dimensions of quantities are represented using a square bracket. So this is what we use to represent it. So let me just write down how do we represent each and every dimension here. So whenever I put like this, whenever I put a flower bracket, I mean, sorry, not flower bracket, whenever I put a square bracket and tell L, that means this is acting as a dimension of quantity. This is going to be clearer in few minutes. Similarly, M is represented as M, time as T, temperature as K, mole as MOL, luminosity as CD, and current as A. Is this clear? Now, moving ahead, to actually understand the concept of derived quantity, let us consider the area. Okay, so area is one of the derived quantities. I have a square here, and the area of this square is given by A into A. So what is this basically? This is nothing but length into length, isn't it? Length into length. So what is length into length? It is nothing but L into L. So L into L will give me L square. So this is the derived quantity I was talking about. So this is, as I've written it under the square brackets, it means that this is a representation of a dimension of quantity. And this particular representation is known as the dimension equation. Dimensions equation. Okay. So this particular expression is known as the dimensions equation. Let us take another example. Okay. As usual, you can see this is a cube. So the faces are A, and A. This is the breadth and this is the height. And what am I missing here? Yes, this is another one. So I have three A's here. So basically the volume is nothing but A cube, which means length into length into length, which gives me L cube. So what is this L cube? L cube is nothing but your dimensional equation. Is that clear? Now this L cube or volume is a derived quantity. Right? Moving further, we have force. So this is one of the most obvious example for a derived quantity when it comes to force, right? So what do we have here? Force is equal to mass into acceleration. What do you mean by that? Mass into length divided by time square, because we know that acceleration is nothing but L by T square, or length divided by twice of time. So what do we have here for mass? We have M. I'm writing down the dimensional equation here, or dimensions of equation here. So I have M under the square bracket into L whole divided by T to the power 2. So basically this is in the denominator. When I take it to the numerator, the power is going to become -2. So I'm going to write down the dimensions of equation as m into L into t to the power minus 2. So this is nothing but the dimensions of equation of force. Is that clear? Nice. Now, let us see the different dimensional equations, right? So what do we have here? Basically, we have volume, right? So talking about volume, volume is nothing but L cube. We just checked it out. So, but then if I have to write it with respect to dimensional equation, which includes both mass and time along with volume or along with length, then I'm going to write it down as m to the power 0, something to the raised to the power 0 is equal to 1. So m to the power 0, and then I have L to the power 3 and t to the power 0. Why is it t to the power 0? Because there's no time factor when it comes to volume. However, when it comes to speed, of course, there's no mass. Mass is going to be 0. So m to the power 0. L to the power 1. Isn't it? We have the factor length there. Speed is nothing but m by s. So that is what speed is, right? So I have L to the power 1 and t to the power minus 1. Why is it minus 1? Because I have seconds in the denominator or time in the denominator. Next comes the force. So force is equal to m into a. We just simplified it just now. So it is m to the power 1, L to the power 1 and t to the power minus 2. Next, we have mass density, right? So when it comes to density, it is nothing but m to the power 1, L to the power minus 3, and t to the power 0. Why? Because density is nothing but mass by area and, sorry, mass by volume. So as it is mass by volume, we have m divided by, or kg divided by, let me write that as kg so that it is going to be easier. So it is kg divided by volume. Volume is already, we know that it is L cube. So I'm going to write it as L cube because I'm trying to represent volume here. So when I simplify it, I'm going to get m to the power 1, L to the power minus 3 and t to the power 0 because we don't have any time component, right? Now, what is that I want you people to do is take down this assignment, and I would want you people to write down the dimensional equation for work done, energy, and I've already given you an equation here, that is F is equal to mgh. You know which equation this is, right? So I would want you to write a dimensional equation for this and for velocity. It is very similar to speed. Okay, so this is the assignment I would want you people to do before you come to the next class. So in the next class, let us learn about the analyzation of this dimensional quantities and the application of it. Okay, fine then. See you all in the next class. Take care.